Atomic structure and mass spectroscopy. When we analyze the amount of different isotopes that are in a particular, or that make up a particular element, we talk about them in terms of their fractional abundance. Fractional abundance, as it says up here, is just the fraction of a quantity of an element that's composed of that particular isotope. It's really the percentage without the times 100. For instance, the fractional abundances of the isotopes in neon are shown here. It shows that neon 20 has a fractional abundance of 0.9051. Its percent abundance then is 90.51%. That simply means that of the neon, naturally occurring neon on Earth, 90.51% of it is neon 20. 0.27% of it is neon 21, and 9.22% of neon is neon 22. That has mass number of 22. So again, these fractional abundance values are simply a percent without the times 100. And notice something else. The atomic weight, the average atomic weight of neon is closer to 20 than it is to either the other two isotopes because of the high fractional abundance of neon 20. So you can look at a lot of the isotopes, or excuse me, a lot of the elements, and determine or get a very good idea of what the most common isotope is just by looking at their average atomic mass. Remember, our average atomic mass is simply a weighted average of all of the isotopes that are naturally occurring for that particular element. For neon, then, we would simply take its mass number of 20 times its fractional abundance and add that to the fractional abundance of neon 21, multiplied together, and then 22, neon 22 with a mass number of 22 times its fractional abundance, 0.0922. When we add those together, we get that average, that atomic mass value, 20.1871 AMUs. Mass spectroscopy is a way that we can get these fractional abundances. We determine the masses of these atoms, these isotopes, by measuring the mass to charge ratios of the positively charged ions that we form from these atoms in the mass spectrometer. Different isotopes are separated by a magnetic field, so if you think about it, depending on how charged they are, it's going to cause them to land in different positions on a detector. So in this case, we're looking at boron. And on the left-hand side, you can see that we've got the relative abundance of boron. And down here at the bottom, we're looking at the mass number, and you'll see that two isotopes of boron pop up, the isotope that has a mass number of 10 and the isotope that has a mass number of 11. And you can tell by looking at the relative abundance which isotope is more common. It is the isotope that has a mass number of 11. You can calculate the atomic mass from these relative heights simply by measuring them. So if you measure the height of the line at 10 for the mass number of 10, let's say you get 1.1 centimeters if you have this on your paper, and the height of the line at the mass number 11 is 4.9. The first thing we'd want to do is to get the total height. So we would add those two together, and when we add them together, we get 6.0. And just like we do with percentages, we're going to do partial over total. So partial over total without the times 100 is going to get us the fractional abundance. So for boron 10, we're going to get its height of 1.1 centimeters divided by the total, partial over total, and we get 0.1833 for the fractional abundance of boron 10. The fractional abundance of boron 11 at 4.9 is the height of that line was 4.9. We're going to divide that by 6 and get a fractional abundance of 0.8167. Remember, that simply means that 18.33% of the boron is the boron 10 isotope, and 81.67% of boron is the boron 11 isotope. Once again, now that we have those fractional abundances, we can simply take the fractional abundances times the mass number for each one of those, add them together, and that will get us the average atomic mass.